So good evening, everyone. Thank you for that nice introduction. As you know, the real world is analog. That is voice, light, heartbeat. Everything is in analog nature. Many of the inputs and outputs of electronic systems are analog signal. And many electronic systems, particularly those dealing with the low signal amplitudes or very high frequency, requires analog approach. And the most challenging design problems are in analog circuits. So today in this session, we'll see the analog IC design flow. And this is the overview of today's session. First, I'll give a brief description about the history of transistors, then the Moore's law, then what's technology new, then a brief description of the fabrication process, and then the analog IC design flow to tape out. So first, we'll see the history of transistors. The first patent for field effect transistor principle was filed by physicist Julius Edgar Linfield in 1925. And then the William Shockley and Gerald Pearson built the operational versions. And in 1956, Bardeen, Walter Brattain, and William Shockley, they got the Nobel Prize in Physics for the invention of this PNP point contact germanium transistor. Later, due to the manufacturing difficulty in using germanium, the industry has switched to the silicon. And then the invention of the MOSFET that led to this new technology era. So what is the driving force for this? The invention of the transistor. During the Second World War, the radar requirements produced a very strong desire to fine-tune solid-state rectifiers, and this resulted in some effort to try to improve the silicon and germanium materials. That time, the radar was based on relatively low frequency or low wavelength that resulted in poor accuracy. So the demand for high frequency radars led to the demand for lower capacitance solid state detectors. In 1926, Linfield invented the concept of field effect transistor. And in 1938, the two Germans, Pohl and Hirsch, described a solid amplifier using potassium bromide. And in 1940, Russell all learned the single crystal silicon can be made as N-type or P-type. And he prepared a sample using that. The top part was P-type and the bottom part was N-type. And when it was exposed to light, it developed an voltage. And in 1947, Bardeen, Brattain, and Shockley invented the transistor, which is point contact transistor and is made of germanium. And they got Nobel Prize for that. In 1950, Brattain, Shockley, Thiel, and Sparks, they succeeded in growing the first junction NPN device. Previously, it was point contact transistor, and in 1950, they developed the first junction NPN device. In 1952, Bell's lab team developed the means of making high purity silicon and germanium crystals by sound refining process. So the concept of the transistors were going on. Parallel to that, this fabrication of this device is also going on. For this, for efficient working of the transistor, we require high purity silicon and germanium crystals for that. So that time, the Bell lab teams developed the sound refining process of making. And in 1952, Ian Rose and George Decade succeeded in making the first unipolar device, that is JFET. And in 52, John Gordon Teal left the Bell Labs to join a company, and it is later named as the Texas Instrument. At the same time, in 1950s, Jack Kilby of Texas Instrument developed the first IC, which consists of one transistor, a capacitor, and a resistor, all together on a single piece of silicon. That was the first integrated circuit. And at Fairchild, Gene Honey developed the planar process for transistor. That is a fabrication process for the transistor. And the first photograph represents the first IC by Jack Kilby, and the second photograph represents the first RTL IC using the planar process developed at Fairchild. And in 1955, the foundation of the Shockley Semiconductor that led to the Silicon Valley. And in 1957, these scientists, these 8 people, abandoned the Shockley, and then they have invented the Fairchild semiconductor. The invention of the MOSFET that happened in 1959 by Mohammed Atal and Dawan Khan. They have successfully 59. And 1968, Bob Noyce and Gordon Moore together with Andy Grove formed the Intel Corporation. Industries, that is Intel, Fairchild, Texas Instruments, and they were parallelly, actually they were competing each other to develop the MOSFET that led to the many that we can include all the functionalities in a single chip, right? So this is the 3-dimensional view of the MOSFET structure, and this is a cross-sectional view of the MOSFET structure. And they have analyzed the small signal model of this MOSFET structure. And from that, they have developed the equation for the transit frequency. That is the frequency at which the small signal short circuit current gain of an intrinsic MOSFET drops to unity. That is the transit frequency, that is the maximum frequency that MOSFET can operate. And from that, they got the relation between the frequency and the channel length of the MOSFET device. And you can see that the transit frequency is inversely proportional to the square of the channel length of the MOSFET. The necessity, that is our requirement, was the high frequency devices, high frequency operation. From this relationship itself, it is clear that if you are scaling down the dimension of the MOSFET can operate at very high frequency. So we can develop high-speed processors from that. That led to the scaling of MOSFET. And you can see that initially the frequency was 5 megahertz. And now at the end, you can see that it is around 4.5 gigahertz. That is, the scaling of the MOSFET led to the increase in the frequency and the device operations. And you can see that the processors with multi-functionalities in that. So you can include more functionalities in a single processor, and that can provide a great advantage in this electronics era. So this scaling of the MOSFET that created a trend. From that, the Gordon Moore has observed something from that, and that is in 1965, the number of components on an integrated circuit would double every year until it reached an astonishing 65,000 by 1975. So he analyzed that in 1965, it was around 50,000, below 50,000, and in 1975, it became 65,000. And from that, he got an idea and he made an observation, and it is the doubling of the transistor on a chip every 2 years. That is, the scaling of the transistor results in the increase in the transistor density, that is the number of transistors per unit area. So from that, the Moore made an observation that became the Moore's law, that is doubling of the transistors on a chip every 2 years. It is just an empirical relationship. Along with that, you can see that the cost per component is nearly inversely proportional to the number of components. So as you add more transistor per unit area, the cost of the component can be reduced. That means you will get cheaper devices. And this is the pictorial representation, graphical representation of the Moore's law. And the semiconductor industry is following this Moore's law. And up to 2000, it was the increase in the transistor count was following the Moore's law. And you can see that the scaling down of the transistor, that means we are reducing the dimension of this transistor. So the source and the drain, the distance between the source and the drain is reducing. So that will create the interaction between the source and the drain regions. So the second order effects will be dominant for the small devices. So the planar transistors cannot be scaled down below a particular limit. So the conventional MOSFET was replaced with the multi-gate transistors to continue this scaling of this device. And new methodologies, new materials have introduced. And you can see that in this figure, 3D semiconductor, then it is moving towards the future. It's representing the future. Maybe this is replaced by the spintronics, then the carbon nanotubes. Then these semiconductors will be replaced by single atom transistors. So the recent scaling of the integrated circuit technology limits the usage of the conventional planar transistor. To continue the scaling of the transistors, the single gate transistors are replaced by the multiple gate structures like tri-gate FET, FinFET, gate-all-around FET. The most challenge is the fabrication of these multi-gate devices and the design complexity. So this is the conventional planar transistor. That's the classical MOSFET. And then we have developed the planar double gate MOSFET so that better gate control over the channel. Then ultra thin body SOI MOSFET, that is silicon on insulator MOSFET. And then the tri-gate and the FinFET. Then the gate all around FET, that the gate wraps around the channel, and the lateral, that is horizontal form, and the vertical form, that is the nanowires. Based on the current research, The future of the transistor sustain in 3D multiple gate device topology, and the Intel has developed the 7 nanometer technology node processors using the FinFET technology. Now, the conventional MOSFET is replaced by this multiple gate devices. So you can see the different multiple gate structures here. And each structure, you can see the first one is a single gate, second one is the double gate. So it has better control over the channel. And this is triple gate. Compared to the double gate, triple gate has more control over the channel. Then the pi structure and the gate all around structure. That's a quadruple structure, surround gate structure. And finally, the gate all around nanowire structure. Now this semiconductor industry is moving towards the 5 nanometer technology node, and the researchers are going on in this nanowire transistors. Now we'll come to the technology node. What is a technology node? It refers to a specific semiconductor manufacturing process and its design rules. So you have seen that the process node, the process technology, or the node you are working on. So different nodes imply different circuit generations and architectures. So it represents the feature size of that. That is the transistor's channel length, or the gate pitch, or the half pitch of the transistor or of the device. Feature size means the minimum length of the MOSFET, that is between the distance between the drain and the source. And it represents the gate length as well as the metal half pitch. But recently you can see that as the scaling is continuing, and we have switched to new process nodes, and for 22 nanometer, 16 nanometer, 14 nanometer, and 10 nanometer, like that. In the recent technology nodes, it represents the generation of the chip in that particular technology node. It's not representing the gate length or half pitch of that device. So driving force behind the process node scaling is the Moore's law. And you can see that to achieve the density, the doubling of the density, transistor density, two factors are there. That is the poly pitch, conducted poly pitch, that is the gate pitch, and the minimum metal pitch. So we have to scale down these two by 70%. That results in the 50% reduction in area of the transistor. That means in a single unit area, the transistor density can be doubled. So you can see that the technology node 180 nanometer technology, it is succeeded by the 130 nanometer technology, and the 130 is succeeded with the 90 nanometer technology. You can see that it is by a factor of 0.7. So this is the scaling principle we are following. And now it's a 5 nanometer technology is going on. The researchers are still going on to 3 nanometer and further technology nodes, new architectures, new device materials. And in all this, the most challenging thing is the fabrication of this device. The scaling down of this device, that means the feature size of this transistor is reducing. So we require equipments that is different, that for the fabrication process, we require equipments that is for the lithography. We have to pattern the device. accurately. So we require more precise equipments. So we have to switch to different nodes. So that is the main challenge in moving from one node to the next node. So this is just a representation of the transistor count. So in the initially, the most transistor technology, the number of transistor in a single chip was 3,510, and the transistor density was 167. And you can see that in 2018, this the process node, and in that 1975, the process node was 8,000 nanometer, and in 2018, it is 7 nanometer. And you can see that the transistor density in that and the area of this chip and the number of transistors in that particular chip. So the scaling of this MOSFET and the new device architecture made this a reality. Now you can see that fast technology. So this computational efficiency, the computation speed has increased, the calculation speed has increased. Now it is in 7 nanometer technology node, and we are switching towards the 5 nanometer technology node. The main companies for currently developing or planning for this 5 nanometer technology node are Intel, TSMC, and Samsung. And the TSMC has already started the mass production of 5 nanometer node, and Samsung has developed a complete design in 5 nanometer technology node. So for, as I told before, we are switching from one node to another. The hardware changes are required for each process node. In reality, the lithography technique decides the next generation. The researches are going on, but if you want to make it a reality, the lithography techniques have to be improved, have to be modified so that it can develop this 10 nanometer or 7 nanometer or more reduced feature size. And the lithography techniques used, the currently used lithographic techniques are immersion lithography with multiple patterning, EUV, and DSA, that is directed self-assembling. So now we'll see the different fabrication steps involved in this device developing. So these are the main steps followed in the integrated circuit manufacture. The first one is the wafer production. That is the silicon wafers. Silicon is abundant in nature in the form of sand, that is silicon dioxide. From that, it has to undergo a lot of processes, and we have to attain a single crystal silicon that is of high purity. That is, the process is named as Czochralski process and Sond refining process. Through that method, the wafer is produced in the desired dimensions, the desired diameter. Then the epitaxial growth, then etching, masking, doping, the diffusion, ion implantation, metallization, and finally the assembly and packaging. So in this step, the fundamental fabrication steps for the generation of the MOS ICs are lithography. That is the process for pattern definition by applying a thin uniform layer, that is a photoresist layer on the wafer surface, and then hardened by baking, and then removing the selected portion by projecting the light through the reticle. that is the information containing in the mask. Then the etching process, that is removing the unwanted material from the surface of the wafer. And then the deposition, that is a film of various material that can be deposited over the wafer by physical vapor deposition or chemical vapor deposition. Then the chemical mechanical polishing, that is planarizing technique. After the photolithography and etching process, we have to polish the surface. We have to remove the unwanted materials from that. For that purpose, we use the chemical mechanical polishing. Then the oxidation, ion implantation, that is doping of this semiconductor, that is by ion implantation or by diffusion. So these are the fundamental fabrication steps that is involved in the MOSFET IC. So this is just a pictorial representation of that. The first one represents the silicon crystal, that is by Chokalski process or by Son refining process. High purity silicon single crystal is developed, and we can slice it and in the form of the wafer. And this is a polished wafer. And in that, you can fabricate the device, and represent the magnified form of this wafer section representing the transistor. And you can pattern to that device using the photolithography technique. Then developing the chip section, etching the unwanted materials from that, then the deposition and the patterning of this device, and finally into the transistor form. So we'll see an example for that. This is the cross section of an inverter, which you can see that this is the NMOS transistor and this forms the PMOS transistor. So this is the wafer, that is a doped wafer, that is P substrate. To that is oxidation. By oxidation, we have developed the silicon dioxide over the substrate. So we want to pattern, we have to create the N-well here. For that, we are going for the photolithography process. First, we'll deposit the photoresist, and then it will be exposed to the light. This is the mask. So the remaining portions are protected, and this portion is exposed, and it will react with the light and this. And here we can etch the oxide with hydrofluoric acid, and then we can implant this N-type dopant into that by diffusion and ion implantation process, and then removing the remaining portions, that is the silicon dioxide. So the N-well is created, and by chemical vapor deposition of the silicon layer, we can create this one. Then the polysilicon is deposited over that. Then again patterning it for that, so that it will create the gate regions. Then again oxidation. Then pattern it. This is a mask. We are patterning it. Then the source and the drain for the P region is created by diffusion. And then we are again going on NMOS transistor and the PMOS transistor. And finally, the metallization. So in this, you can see that the lithography process, etching process, deposition process, And the implantation process are the repeating process in that, and the chemical and mechanical polishing. So these are the some of the fundamentals of this fabrication process. From that you can develop the transistor. So as we scale down the transistor, this fabrication steps becomes more complex because the accuracy is the main factor while etching the device or etching the portion from the transistor. It has to be very accurate, otherwise it will affect the performance of the device. So there are some simulation tools are there for device modeling and characterization, that is Sendoros tool and the Atlas Silvaco tool. In that, the materials are provided in that you can model any device, any structure, and you can characterize it before going for the fabrication. So this is an example. That is a process simulator. You can develop the any device structure in that. You can analyze it. So in that, the deposition process, all the fabrication steps, you can simulate in this tool. You can develop the required structure. So I have shown the gate all-around FET structure, a portion of that developed in the Sendoros tool. And final, the 3D cylindrical GFET structure developed in the Sendoros tool. You can see this one. And you can characterize this in this tool. So if you need any modification, you can go back and do this. The fabrication steps again, you can characterize it. And once you get the required specification, you can go for the fabrication of the device. So you can do the electrical characterization in the simulator, and then you can go for the physical fabrication, then the characterization of this device, and from that you can extract the parameters and you can develop a compact model for that device. So coming to the model, the MOSFET transistor model for the integrated circuit design is the BSIM model. That is a planar transistor model. That's commonly used, which is showing an accurate results with the fabricated fabricated device, that is developed by the Department of Electrical Engineering and Computer Science at the University of California, Berkeley. They have developed this model, and using this model, we are designing the circuits, we are simulating the circuits and analyzing the response, and we are going for the fabrication of the circuit. So till now we have seen the back end of the design. And this is the BSIM model for a transistor. So we can use this model for our simulation. So now we have the SPICE model or the BSIM model with you. Now we can go for the analog IC design. So till now we have seen the back end of the IC design, that the device is create device fabrication and everything. So from that we'll get from the feature extracted, from the parameter extracted file, we can create the model. And using that model, you can go for the circuit design. And you can implement your circuit. For the analog IC, so you can see that for analog IC design differs greatly from the digital IC design. In digital IC design, it is mostly done at an abstracted level with systems and processors that determine the specifics of the gate or transistor level, placement and routing. In analog IC design, it generally focuses more on the circuit, especially on the sizing and the specific that the parameters of each transistor. So these are the some of the factors that we have to consider in designing an analog circuit, and these are interrelated. There are trade-off among these 8 factors. So you have to design a circuit with respect to the constraints, the specifications. If it's an area constrained application, then you have to consider more focus on the area. We have to reduce the area. So you have, then it will affect the linearity or gain of this circuit. So there is trade-off among these elements. So according to our specification or requirement, we have to select the design procedure. So for the analog IC design, the first step is the concept. First, what you are going to of that. Then you can develop the block diagram of that. This is done by the system engineer. So once the block diagram is ready, it will be handed over to the analog engineer. The analog engineer will analyze it, will design the circuit that matches for this specification, and will do the simulation and will recheck it and will redesign it. And once it meets the specification, it will be handed over to the layout engineer. The layout engineer first convert the circuit, will draw the layout of that circuit, that's the layout generation. Then the next step is the design rule check. There are some rules list are there. So it has to follow the rules that the distance between the metal lines and the metal width, the design rules and density of the metal in that particular layout. Some set of design rules are there. So we have to check that. Once it satisfies everything, then we'll go for the layout versus schematic check, that is LVS check. In this, we will compare the schematic with the layout, whether all the terminals are there, whether it is matching with the if it satisfies all these conditions, that is the DRC check, LVS check, and the antenna rules check, then we can go for the parasitic extraction. That is the parasitic element extraction from this layout. So this is the job done by the layout engineer. And after this extraction, the layout along with this parasitic extraction file will be given to the analog engineer, and he will do the post layout simulation. And he will compare with the specification and with the pre-layout simulation. And if there is any discrepancy in that, then again we have to change the layout. Again we have to go through all this process. Then again we'll do the post layout simulation. And if it doesn't meet the requirement, then we have to go for the redesigning the circuit and check the result. So this loop will continue till we'll get the expected result. Once you got the expected result, then you can go for the placement. That is done by the layout engineer. So different blocks will be there. So in an IC, there will be analog section and digital section. And now previously it was, most of the portion was analog. Now you can see that the analog part is only the 20% of the whole system. The remaining 80% is the digital system. And for the digital system, there's a lot of switching processes are going on in that. So we have to isolate this analog and the digital part. So the placement of this blocks is an important point. So you have to place each block in a particular position so that the interaction that the integrated system won't happen. And routing, then we'll go for the dummy filling, that is the density that depends on the foundry. You can see that four metal layer process, 7 metal layer process, 14 metal layer processes are there. So different metal layers are there. In each metal layer, the width and the thickness of the metal layer varies, that the resistivity of that metal varies. So this device has to undergo a lot of fabrication process. So it has to withstand lot of temperature and all this physical and mechanical processes for reliability. Then again, we have to go for the design rule check and then the LBS check. Once this is ready, that is LBS check is clean and the design rule check correct, then we can export this to the GDS file. So this is the steps done by the layout engineer. Now this GDS file will be handed over to the system engineer. He will submit this to the foundry, and then the foundry will do the physical fabrication of that, and will get the IC in the form of die. So you can, from the die itself, we can measure the parameters from that. And if we are getting the expected result, we can go for the packaging and assembly, and finally you get the IC. So this is the flowchart of that. You can see that the concept or idea, the specs definition, and the architectural block definition, it may take 1 to 2 weeks. Then the schematic design and the simulation, it may take 3 to 6 weeks. And then the layout generation and the DRC, LBS, antenna root check, and the PEX extraction can take 1 to 3 weeks. This is only for the case those who are experienced in that, they won't take much time. If you are fresh, if you are first time, if you are doing it, it may take months to complete these steps. And then the post layout stimulation and then verifying the results. If it is not matching with the expected result, then again you have to redesign the circuit, and again you have to undergo the same procedure. Once it is ready, then we can go for the floor planning and the placement, then dummy filling, DRC and LBS, and you can export this to GDS2 file, and then the submission. Then this is the backend process, that the physical fabrication of this device. So from this GDS, they will extract that file, and then they will create the mask in the foundry for the particular design, and then it will undergo the different fabrication process, and we'll get the chip, we will get the die. And if it is not matching with our expected results, then you have to again redesign from the starting point. You have to start from this point itself. So these are the important steps involved in the IC design. So this is the first, the concept or idea and the block definition, and we have In the cadence tool, you can create the circuit there and you can do the simulation there. And then if you are getting the expected result, then go for the layout. So as this is the work done in NIT Calicut. This is the OTA structure, OTA circuit diagram, and this is corresponding layout of that. And here we haven't considered the area. It's not an area constraint one, so you can see the lot of vacant spaces are there. And when you place this whole circuit in that floor, you can see that you can arrange this each blocks in a particular fashion which minimize the interference. Then we can go for the DRC check, that's the design rule check. For that we can use the caliber tool, which is the software from the Mender Graphics. So in that tool, the rule sets are already attached with that. The foundry will give the tool set that the technology is with respect to that technology node. So in that you can do the DRC check in the caliber tool. And you can see that here some errors you can see in that. This represents the density errors. So in the initial stage, you can neglect this error. If there are errors like this, then you have to consider that there will be some violation in the design rule, that the distance between the metal lines, or there will be some overlap of the metal lines. So you have to go through that and you have to redraw the layout and you have to minimize the errors. So in this, the density errors, you can neglect it at this point and you have to remove all other errors in that, in the DRC check. Once it is ready, then you can go for the LVS check, that we are comparing the layout with the schematic. The caliber tool itself, we can do the LVS check. It will check whether the connection between the components are exactly as in the schematic. So it will detect any electric short in the circuit, in the layout that we have created. And then we'll go for the, if once it is correct, we can go for the antenna rules check. And it is antenna effect means the plasma induced gate oxide damage. That is, you can see that if you are connecting the gate like this, while fabrication process, there are chances of the oxide breakdown of this polysilicon. That is the oxide breakdown in the silicon dioxide. To avoid that, we have to follow the type of methodology in that. Instead of directly connecting from one metal to this polysilicon, you can go like this. That is this is the driver, that is one transistor, this is the another transistor. So this is the polysilicon. From that, you can take connection using the metal one, and this in between you can see this is the via, and from metal one then to the metal two, and from there you can go for the connection to this load. So this gate oxide breakdown can be avoided if you are connecting like this, or you can connect a diode here to avoid the breakdown of this devices. So the antenna rules check will check this topology, whether it is violating this, whether it can cause any oxide breakdown. If during the fabrication process, if there is any oxide, if there are chances of that, and in while working of this chip also, there are chances of that oxide breakdown. So we have to avoid that. So while doing the layout, you have to consider that long wires in a single metal layer is not desired. So this type of topology is desired for the metal connections from one point to another point. So this antenna rules check will check all this consideration, and once it is correct, then you will get this window like this. That is the antenna and the bonding wire rules are correct. That ensures more safety for this devices, and this the chances more chances for the working of this circuit. Then we can go for the parasitic extraction. In the same tool itself, we can do that PEX run in that tool itself. In the using caliber, you can do that. So that will generate the parasitic components in from the layout. That is the resistors, capacitors. If you want inductors, you can include that also. Components are also you can include in the simulation. That will give you the actual result of that circuit, actual performance of that circuit. So after the parasitic extraction, we'll go for the post layout simulation. Then the next step is the floor planning. That is after once it is everything is correct, then we can go for the floor planning. So here I have just represent the single block, that is single OT is placed in this one, and these are the IO pads. IO pads means input output pads and the supply voltage pads here. So this is the, from this IC you can take the connections to this pad, and this will convey this signal to this external board through this IO pads. So the input and the output signals will be passed to this circuit through this IO pads. So you have to place this IO pads in a proper position. So the foundry, they will give you the dimension of the complete IO pad frame. There will be standard sizes for that, the length and the width. According to that, you have to create this frame. Here I have just shown the in between you can see the spaces are there. You have to fill with the filler pads here. So again, you will get a complete IO pad frame, and inside that you can place this transistor and you can make the connections to this IO pads. So this will be the external interface to this circuit. So now you can see there are lot of vacant spaces are there. So if we are directly giving it for fabrication, then you can see that the density issues are there that may damage this device. To avoid that, you have to fill the vacant spaces with the dummy elements. So that next procedure is the dummy fill. So the previous layout, it is not filled 100% with each metal layer. So during the fabrication, it is desired that all layers are more or less equally filled. So for that, this dummy fill script is created for that, so that it will analyze this layout, analyze this IC, and it will generate a script, and it will automatically layers into the IO pad frame. And then we can go for the DRC rule check. And in this, at this time, you can see that the density errors are solved at this time. So in the DRC, in the previous section, you have seen that in the DRC check, there was some density errors was there. So in this, after the dummy filling, you can see that all that errors are solved. So you will get a clear report. So this is the picturization. You can see before dummy fill, it looks like this. So you can see the vacant spaces there. And after dummy fill, you can see that all the metal layers are filled so that you will get the equal percentage of all the metal layers. That ensures more reliability of this IC. Then the last is the last DRC and the LVS check. And if everything is correct, then you can go for the fabrication. And this foundry, they might have given you the seal ring, that is the boundary for this one. This is, you can see that, you can see the complete IO pad frame in this, and the bonding pads, there have given some rules for that. The placement of these bonding pads, you have to keep that minimum distance between these pads. And you can see that this the outer boundary that represents the seal ring of this IC. And this is for, you can see that in this wafer there will be lot of different charges will be there and different dies will be there, right? So while cutting these dies, it should not affect the IC. It should not enter into this one. Cut this dicing. So you'll get the die from that, from the wafer after the fabrication. So before this you can insert the serial, then the serial number, that is the IC number that you can insert inside this layout. That represents, that indicates that this is your die. And then go for the physical fabrication. So it will undergo all this lithography process, oxidation, deposition, etching, and all the process will undergo and will get the final product, that is the die. And you can measure the parameters from this die. And if it is working, then you can go for the packaging of this die. And then also you have to consider, there also you have to look into it, which for packaging, and you have to find the packaging industry for that. So this is just the three-dimensional view of the GDS2. That is, we have the layout, we have converted into a GDS file, right? That is a database. And if using the GDS2 viewer, that is a 3D viewer, you can visualize this layout in the three-dimensional form. So you can see the different metal layers and the different devices beneath that. These are metal layers. So you can visualize it, your design IC. You can see the different layers, the metallization layers there. And then once you have fixed the packaging, the number of pins and the type of packaging, then you can approach these packaging people. They will give you the bonding diagram for that. So you can embed this IC with this bonding diagram. So you can see that this, from this IO pads, you can see the connection towards this bonding pads. And this is the packaging pins. So different types of packages are there, surface mount package and through hole package. So the surface mount, you can see that QFN package, QQFE, SOP package, and the through hole. We are familiar with this one. You have seen in the labs, DIP package, different type of packaging that depends on your application. So the first one is my IC, that's the IC which I have done the tape out. This is the QFN package with 32 pin. Or you can go for the through hole packaging. Then you have to test this IC. After the packaging, you have go for the testing of this IC. For that, you can do the PCB design. For that, you can use the KitKat tool or any other softwares in that. I have used the KitKat tool and I have made this PCB design in that for testing my IC. And finally, the testing and the verification of this performance of this IC. So this is the analog IC process flow. So in that, in the back end, you have seen the fabrication process of the device. So if you are using the new device architectures, then you have to use that device models in your design. With that, you have to design the circuit and do the simulations for that. So if you want to do your circuit design in a new device architecture, you can go for the first you can model the device and you can extract the parameters from that and develop a compact model for that, a spice model for that, and then you can go for the circuit design and can do all these steps, and final product you can test it and verify it whether you are getting the expected response. So this is a short video of the fabrication process. So you can see this one. So you can see that from the sand, we are that is a silicon dioxide. So we undergo this silicon dioxide, this sand into different processes, and by Czochralski process, we'll get the high purity silicon. This is a silicon ingot, and from that we'll slice it, and the wafers are ready for that pure silicon wafers. In that wafer, you can fabricate wafer. That's photolithography process. So this is the device development stages, different stages, and the metallization. And then slicing this wafer. And then the packaging. One more is there. This is the detailed flow of the fabrication flow. You can see that.
You are about to experience a fascinating journey through the clean rooms of the semiconductor industry. See integrated circuits in the making at one of Global Foundries' chip factories.
So this is a clean room where we'll do the fabrication of the IC.
A world that normally remains hidden from our eyes. In the beginning is the circuit diagram.
So the first step is the idea, the concept development, and then the circuit designing.
Circuit diagrams, sophisticated integrated circuits like microprocessors, high graphic processors, and wireless communications ICs. The next step is manufacturing. Disk substrates for the microchips are made from quartz sand and are called silicon wafers.
So these things you have seen in the previous video. From this sand, we are creating this pure high purity silicon.
A huge monocrystal raw drawn from purified silicon melt. The result is a perfect silicon lattice into which the transistors will later be fitted. However, impurities pose a threat to these flawless silicon crystals. Our global foundries manufacturers must therefore take extensive precautions every time they enter our dust-free clean rooms. The result? Our wafers are fabricated in an environment that is more than 100,000 times cleaner than an operating theater. Completely free of dust, the silicon discs arrive at the clean room. Here, 25 wafers are packed into each hermetically sealed container and sent off on a journey that will take them through hundreds of manufacturing steps.
So this is an automated process, this lithography, oxidation and everything. All
Photolithographic
the
techniques
fundamental
transfer the circuit structures to the
fabrication
wafers,
steps.
rather like slide projection.
All the
The key
steps
to
are
this whole
undergoing
process
in the
is the
clean
subtle
room.
mastery of light.
A small impurity can damage the device performance, that affect the device performance. So this
The silicon disc is spin-coated with a photosensitive resist. UV light transfers the circuit structures depicted on a mask to the wafer. The exposed parts of the resist are soluble and are removed by a developer. The transferred structures can now be used as a template. The unprotected parts of the water surface are etched away. The structures of billions of small current switches are generated on each wafer, tiny transistors. From the photolithographic stage, wafers move on to the ion implantation, where the electrical properties of the transistors will be specified. Here, the engineers make good use of one of silicon's most important properties. Silicon is a semiconductor, which means that its conductivity can change via a high precision emplacement of so-called dopant atoms. First, dopant atoms are injected into the silicon structures.
this is the doping process,
These atoms then distribute randomly in the silicon lattice.
that is by ion blindation
At high temperatures,
or
the doping
diffusion
atoms become
process.
flexible, take on a fixed position in the atomic structure. The complexity of manufacturing tiny transistors requires a clean room as big as 2 soccer pitches. While our people monitor the complex processes, automated manufacturing itself always takes place within hermetically sealed production lines. Copper dominates the next process step. The finest interconnect wires link up billions of separate transistors to form integrated circuits. Before that can happen, however, cleaning is essential for wafers, as particles lurk at every stage in the manufacturing process.
There is a chemical mechanical polishing.
Before the copper is poured into the trenches for the interconnects, a barrier layer is applied. It helps to avoid short circuits and guarantees reliability. The trenches are then filled with copper. Finally, the excess copper is ground down to the edges of the trenches.
That is the polishing
This
of the
insulates
surface.
each interconnect from the others. A microchip made of copper wiring established GlobalFoundries as the first company in the world to adopt copper in volume production. A foundation for the state-of-the-art multi-core processors that GlobalFoundries is introducing today in all product areas.
So at each process
To keep
level,
on
they
some
will
of the
check
leading edge
the
of the world's chip makers, electron microscopes constantly
using the
monitor
electron
every step in the
microscope. They will
manufacturing
check
process.
the dimensions
Down
and
to the atomic
everything,
structures of each individual transistor.
whether the etching is perfect, the oxidation is perfect, the lithography, everything, the mask.
In 2 months, link up 100 billion transistors on numerous levels. And that in a space no larger than a fingernail. GlobalFoundries, the first truly global semiconductor foundry, located in the USA and Germany. Fab 1 in Dresden and the future Fab 2 in Malta, New York. Together, they'll be two of the most advanced chip factories on Earth and a testing ground for the very latest microelectronic innovations from around the globe. The last production step in microprocessor manufacturing is the packaging of the chips. In preparation for this step, tin silver pellets are applied on the wafer. They will link the chip to the frame. Via the finest saw blades, the chips are cut off the wafer. The flip chip method is used to bond the chip to the frame, which is sealed with a cover.
So that's all about the analog IC design flow. So any questions?
I have one question, ma'am.
Yeah,
How long will it take to manufacture a processor, maybe a normal
process.
processor?
If it is an initial from the initial stage means then it may take months, because if it is like if you are designing a new one, then it will take a lot of time for that, because the design first you have to freeze the design, then this layout, and if it is matching with the layout and all, we are getting the post layout simulation and everything, then you have to freeze the design, then we'll go for the fabrication. So the designing part takes the time. If once the design is ready, then the fabrication won't take much time. It will within 3 or 4 months you will get the icing.
Okay, ma'am. Yeah.
In the Mender graphics rule check, can we add our own rules? It's predefined rules are there. We can't change that rules in that. It is the rule file is generated or created by the foundries. So each fab, they have their own design rules will be there. So according to that, they have generated that design rule check. So you have to, if you are using that particular package, that for my design, I have used the SCL 180 nanometer technology package, that PDK file. For that, we have to follow that design rule check. How the doping quantity is set? Uh, you mean the doping the per centimeter cube like that, or? So for each one, for the doping, it will result in the resistivity of the device, right? So we have to ensure that what resistivity you require for that. So from that, you can choose the type of doping, that is maybe ion implantation or the diffusion. So the you have to go for the acceleration and the heating of that. You will do some procedures there. With ion implantation, you can there is an acceleration velocity for each ions, so you can implant that and that will decide the depth and the concentration of the doping concentration there. If you are going for the diffusion, it is entirely different. So depend on the requirement, that if you want it is to dop in the depth, then you have to go for the ion implantation, and there's number of ions striking that surface, it is counted. Any other question?
If you guys have any more questions, feel free to ask it in the chat box, or you can unmute yourself too.
Decided by the system engineer or the analog? It is decided by the foundry people, because we are using the analog engineer, he or she will be using the compact model, that is the spice netlist model, that is there in this that we are following or that we are using. So in that particular nanometer technology, that doping concentration, everything will be fixed. So if we are going for this particular model or this particular foundry, they have some specified doping density or doping concentration for that particular device. They will follow that. So it's not decided by the system engineer or the analog engineer. It is decided by the physical fabrication people, that is the people who have developed that device.